Hi everybody, welcome to another video in linear algebra section 6.5 list-wise problems. If A is an m by n matrix and B is vector in Rn, list-wise solution of the equation Ax equal to B is an x hat in Rn such that B minus Ax hat less than or equal to B minus Ax for all x in Rn. So here we have the scenario here. We have vector B and Ax could be a bunch of other vectors. We try to find the shortest distance from B to the plane that contains an Ax. So we try to find the x hat such that Ax hat is closest to B. Right. And to solve that equation, it is equivalent to solving the normal equation of A transpose A, x equal to A transpose B. If A transpose A is invertible, then multiply that both sides. We have x sorry, this would be the hat. I forgot the hat here. So x hat equal to A transpose A, multiply that inverse on both sides if it exists, and then we have A transpose B, and this is called the pseudo inverse of the matrix A. Like that, if this is invertible. Right. Next, find a least square solution of the inconsistent system Ax equal to B. Right. So first we compute A transpose A. So this equivalent to, so Ax equal to B is coincide with A transpose A x hat equal to A transpose x A transpose B. So pretty much we multiply transpose of A on both sides. Right, so let's do that. I'm enter the matrix A, 3 row 2 column. I just want to write A transpose, so I just enter the matrix first. So hit enter, so then I just say A transpose A. Sorry, transpose here. A transpose A, right? That equivalent to 17, 1, 1 and 5 times x hat, and we have A transpose. Once again, this matrix transpose times B to 0, 11. So I'm just actually just write that for once. 19 and 11. And then of course we just do reduce row echelon form. So we have 1 0 0 1. So we have x hat is equal to the vector 1 2. Right. Now let's compare this to other solution. So what do we have? Right. Now if we solve the equation ax equal to b, what do we have? For this system we have the romantic matrix 4 0 0 2 times x equal to b 2 0 and 11. Right. Let's do the reduced row echelon form of the romantic matrix. By the way, it said inconsistent, that means there's no solution. But let's just show that it actually is no solution. Right. Reduced row echelon form. Right. Because we have the pivot on the last column, so this is no solution. So when we solve this system of equation, we have no solution, but we come up with a solution that is as close as possible to ax equal to b being true. So with x hat equal to 1 and 2, we have the difference between ax and b get as close as possible with x equal to x hat. Of course, if there is a solution in the system, then with doing this will give us the exact solution as well. But in this case, that's what we have. Also one more note, when we write the equation like this, and if A and A inverse, if A transpose A exists, then we just use the pseudo inverse. So enter the matrix A. Let's do that again. Right, and now we have, that is A transpose A inverse times A, which is answer, and then times the matrix B, which is 2 0 and 11. Sorry, I forgot to transpose. So A transpose A of that inverse, and then times A transpose times B, and do that we have 1 and 2. Yeah, of course when the inverse exists, when the A transpose A is invertible, we can just use the formula, but not always the case. If it's not always the case, when we just write like this and do reduce to echelon form, we can also find the solution there. The inverse, using the inverse is not the best way to solve the equation. It's not the most efficient way, even though when we write on paper it looks convenient when we use inverse, but in reality inverse is a very inefficient way to calculate. Right, now find least square solution of Ax equal to B. So that A is that B. So once again, the normal equation, multiply the transpose on both sides of that equation. So that's simple enough, right? Let's put a hat on it. Right, and now we just do A and A transpose, and then A transpose B. Right, so I can enter the matrix, but since we use the matrix a lot, we can also store to a matrix. So this is like when you use in the TI-83, you use in this second matrix. Edit, let's store into the matrix A. That's 6 and 4. 6 rows, 4 columns. That's going to be a while. 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1. Oh, I see the pattern here. Right, enter the matrix A. Now we just use names. You see the matrix A, so we have A, transpose A. Right, so A times A transpose A transpose is 6, 2, 2, and 2, 2, 2, 0, 0. I also see the pattern here. X, and then we take A transpose times B. By the way, let's see if this is invertible. It's not. That means we have to do this by hand. Right, so we have the matrix A. I transpose that. Then multiply to the other side. B, which is, oh, good thing it can go up to 6. 6 row, 1 column. Right, that's good. -3, -1, 0, 2, 5, and 1. 4, -4, 2, and 6. Right, now let's do reduce for echelon form of this. Be 4 rows, 4 columns, 5 columns. 6, 2, 2, 2, and 4. 2, 2, -4, 2, 2, me just write this down first. Right. So we have one, those are the pivot, and look like x4 here are free. Right, so let's write that x1 plus x4 equal to 3, x2 minus x4 equal to -5, and x3 minus x4 equal to -2. And x4 is 3. So the solution x hat equal to, so for x1, so we subtract x4, 3 minus x4, and -5 plus x4, and -2 plus x4, and x4 is 3. So we write the solution as 3, -5, -2, and 0, plus x4, factor out -1, 1, 1, and 1. Right, so we have infinitely many solutions. Right, so that's why when we write, we use the pseudo inverse. It will not work because the inverse does not exist. Right. Now, solution to the general least square problem. Let A be n by n matrix. The following statements are logically equivalent. The equation has a unique least square solution for each b in Rn. The columns of A are linearly independent. So if the columns of A are linearly independent, then the matrix A transpose A is invertible. So all of them are equivalent. When all of that are true, then x hat is equal to this. And of course, we define this A transpose A of that inverse times A transpose. This is the pseudo inverse of A. Yeah, the matrix A here is not going to be might not be a square matrix. So only square matrix has an inverse. So that's why we define this as the pseudo inverse of the matrix A. When the least square solution is used to produce Ax hat, an approximation to B, the distance from B to Ax hat is called the least square error of this approximation. Right, next, I'll find the least square error in example 1c. So example 1c, now we have the solution. Okay, so let's go with the middle. So what we have on the previous is that the distance from B to Ax hat is called the least square error. So how do we write that? So distance of B to Ax hat is just the norm or the length or the magnitude of B minus Ax hat. So just going to do that. So simple enough. So least square error equal to distance from B to AX hat, which is equal to the norm of B minus AX hat. One, two, which is X hat, which is not what we have, sorry. Right, B, where's B? Okay, 2, 0, 11 minus AX hat. Right, so we have 2, 0, and 11. Subtract row times column. 4 times 1 is 4, 0 times 2, 0, 0 times 1, 2 times 2 is 4. And 1 times 1 is 1, 1 of 2 is 2, so that's 3. Of course, we can just write a vector in many different ways. 2 minus 4, 0 minus 4, and 11 minus 3. Yeah, just the length of that vector. Of course, we can write a vector in many different ways. So I choose to write like that. And then, of course, it's just going to be 2 square so 2 square is 4, 4 square is 16, and 8 square is 64. So square root of 84. Right, so it's very straightforward, right? Just B minus AX hat. Right, next, find the least square solution of AX equal to B for this. So once again, from AX equal to B, multiply by A transpose on both sides. We have the normal equation, but put a hat on it. So A transpose 8. Four rows, 2 columns. 1, 1, 1. Minus 6, minus 2, 1, and 7. Right, let's use the pseudo inverse this time. Solution is what? X hat equal to A transpose 8 of that inverse. Multiply on both sides, and then we have this. So that is A transpose A of that inverse, and then A transpose times B. Negative 1, 2, 1, and 6. 2 and 1/2. just going to put all of that in the calculator. So that's 2 1/2. Right, now the question here is, how do I know for sure that the pseudo inverse exists? Well, that's what we have from the last part of the theorem, last theorem on the previous page. It says that when the columns of A are linearly independent, then A transpose A is invertible, right? So look at the columns of A, 1 1 1 1, -6, -2, and 1 7. We have two vectors. They are not multiple of each other. They are not multiple of each other, so they are linearly independent. And when they are linearly independent, when the columns of A are linearly independent, the pseudo inverse exists because A transpose A is invertible. So once again, the column of A linearly independent, so the A transpose A is invertible, so the pseudo inverse exists. So in this case, I just enter everything, and we have the pseudo inverse, and we have the solution. Right. Next. Note, if the columns of A are linearly independent, and the least square solution can often be computed more reliable through the QR factorization of A. However, we did find the QR factorization done by hand is very impractical. So in that case, unless we can program it to let the computer do calculation for us, we're just going to use solve the normal equation, and if possible, use the pseudo inverse. Like I said, the inverse sense when we do the regular inverse is a very inefficient way to do it by hand or by computer. So that's why we rarely calculate the inverse by hand if it is more than 3 by 3. Right. Now, however, we just have all the theorem here. If m by n matrix A is linearly independent columns, let A equal to QR be a QR factorization of A. Then for each B in Rm, the equation has a unique least square solution, and the solution is given in this form. Like I said, I mentioned on the previous section, there's a lot of application for the QR factorization. However, none of those we can do by hand in the practical way. Yeah. So, of course, that from the, if we don't want to deal with the inverse, we're just going to use in that and use reduced row echelon form. Of course, reduced row echelon form is always a more efficient way than to use the inverse. Right. Next, for the least square solution of this one. Of course, I'm not going to use the QR factorization because that takes a lot of work, and it's not an efficient way to do it. Right. So once again, we have the equation. Multiply A transpose on both sides. We have the normal equation. Right. Let's find 8. Time the matrix A, 4 row 3 column. When there are 3 vectors, I cannot see if they are linearly independent right away. Right, so that is matrix A. Just hit enter, so I store that into the answer. And then we have A transpose A, so A transpose A. 4, 8, 10, 8, 20, 26, 10, 26, 38. Does this have an inverse? Oh yeah. So this problem we can use the pseudo inverse, but let's just do that first, and then multiply by x hat equal to A transpose. If we hit A now, that could be a problem. Just go back to the original. That is the matrix A, right? And then transpose that, multiply by the matrix B. 3, 5, 7, -3, 12, 12, 20. That would be a unique solution because the A transpose A is invertible. Right. Just do reduce to echelon form. Of this system. 4, 8, 10, 12, 8, 20, 26, and 12, 10, 26, 38, and 20. So if we do reduce to echelon form, we have 1, 0, 0, so the least square solution 10, -6, and 2. Of course, we can also use the pseudo inverse. That is the matrix A, so A transpose A of that inverse times A transpose times B. Okay, first we have the same thing. I write a little note here. Since A transpose A is invertible, the solution is given in pseudo inverse. Multiply the inverse of that on both sides. Right, so we can just use that directly. Right. Next, find a least square solution of AX equal to B and compute the associated least square error. Now the problem was this different than any of the problem that we did so far. What is the difference here? This is the square matrix, right? So if it is the square matrix, that means we have all of those vector A in the same space as this. So the bottom line is the least square error, the least square solution is the same as just the solution. So the normal equation in this case is not necessary, but nevertheless, we just do that anyway. So let's just solve the equation in a normal way. So first of all, let's solve that directly, because this one I solve that directly. Right. One. Right. 1, negative 3, negative 3, 5, 1, 5, 1, negative 3, 1, 7, 2, negative 5. Right. 1, 0, negative 1.5, 0, 1, 0.5. Of course, we can use fraction, but decimal is simple enough. We're just going to stick with decimal here. So we have what? X1 minus 1.5 x3 equal to 2. X2 plus 0.5 x3 equal to negative 1. And x3 is 3. Right, so we have x equal to x1, x2, x3. X1 is 2 plus 1.5 x3. X2 is negative 1, subtract 0.5 x3, and x3 is 3, so x3. So we split, and we have this solution. Because x5, x3 can be any number. Right. That is, we solve it directly. Now let's solve using the normal equation. Just multiply the transpose on both sides. Right. So we just solve the normal equation. 8 transpose times 8. Right. So multiply by transpose on both sides. So we have the matrix A transpose times the matrix A. Yeah, this one doesn't have the unique solution, so for sure the pseudo inverse does not exist. Right, so we have the matrix A again. Transpose that times the matrix 3 B 5 negative 3 negative 5. So I have negative 3, negative 65, and negative 28. Right, let's do the reduced for echelon form here. Let's just write out. Right, 3, 9, 0, negative 3, 9, 38, 28, and negative 65, 0, 28, 14, and negative 28. I have to pause the video and check one thing. Right, I see where the problem is. I just enter it wrong. Right, these are the matrix 3, 9, negative 3, 9, 83, 28. Earlier I entered 38. That was not right. It come out very nice, but it's not the right answer. Because we know for sure this we should have infinitely solution, and it should be exactly like that. Of course, then in this case, then we say similar to the previous. We don't have to do all of that again. So we just say x hat equal to 2, negative 1, and 0 plus x3 1.5, negative 0.5, and 1. Right. Now, compute the associated least square error. So the least square error is b minus ax hat so b -5, -3, -5 minus a x hat. For simplicity, just choose x3 to be, because we just want the error, just choose x3 to be 0. So we just have that. The matrix A is what? 1, -3, -3, 1, 5, 1, 1, 7, and 2. and then we just use this matrix. Right. So 3 and 1, 5, -3, -5. Subtract the matrix. One, -3, -3, 1, 5, 1, 1, 7, and 2, and then times the matrix at hat. Okay. Didn't know we can enter the loop, the matrix inside the matrix like that. Right. 2 and -1. Right. Do that and we have a 0, 0, 0. So what does that mean? In this case, as we see, the exact solution in the normal equation, the equation and the normal equation are the same. And so in this case, that's why we said if we have the vector that is inside of the space. So imagine we find if B is not in the same as AX, but in this case, when AX is the same thing in the same space, then in that case, it's just the equation the same thing as the normal equation, and of course that will be 0. And furthermore, we can just choose a different x1, for example here, for different x3. I mean, if we choose x3 to be 1, so here we have 1.5 plus 2, that will be 3.5, and then -1 minus 0.5, -1 minus 0.5 is minus 1.5, and 0 plus 1. So that's why we can choose any x3, and the distance is always 0. So that's why it is infinitely many solutions. Doesn't matter what we choose, the least square error is always 0. So we have the perfect solution. So here we choose x3 equal to 0 just for a simplification. Of course, x3 can be anything. The least square error is still 0. In that case, we have the exact solution of x and x hat. Right. So with that, we finish section 6.5. Pretty much just least square problems, and so we try to minimize b minus ax, and in ideal condition that is equal to 0, and then we don't have to minimize the error. But if we try to minimize that b minus ax, the solution is x hat, which is coincide to the normal equation. And when the columns of A are linearly independent, A transpose A is invertible, so we can find a pseudo inverse. But other than that, it's very simple, just normal equation, solve for it. And if the equation, the least square error is 0, then the solution x hat is the same as x. Right. With that, we end section 6.5. Thank you for watching, and see you in another video in linear algebra.